Hey, what's going on, everybody? This is JJ, and in today's video we are going to have a primer or introduction to linear algebra. And linear algebra is just the study of vector space structures. And as we can see here in this first image, we have an example of a vector space, or two examples, where we have several vectors that are supplanted on a coordinate system. And this coordinate system always has to be Euclidean space. It cannot be non-Euclidean. And then we can perform many different operations and applications using these vector spaces. And it gives rise to vector fields. And a vector field is just a vector at every point in a given region of space, or whatever the region we are interested in is, which is usually space. And so this is very valuable in physics, and in fact over the next few videos I'd like to work through linear algebra in a physics context, specifically involving Newton's laws of motion. But we didn't have vector spaces right away. Linear algebra took many centuries to develop, and it started with René Descartes, who gave us Cartesian geometry, which is plotting points and lines and planes on a grid, and that grid is usually an x and y axes in two dimensions. He also began to describe linear equations, where we used algebra and symbols and notation to represent lines and planes. But he wanted to take this further and solve these linear equations. So Leibniz came along in 1693 and Kramer in 1750 and actually kind of made progress that didn't really make chronological sense. It was an advancement that should have been preceded by the work of these gentlemen, which I'll get to in a moment. But they discovered determinants, and these determinants allowed them to solve systems of linear equations. And it's very complicated. And they did it without using matrices, because the matrices hadn't been developed yet, which is why I said that they sort of leapfrogged the development of linear algebra. What should have came before them, and their great wisdom and knowledge, was James Joseph Sylvester's expression of a matrix. He gave us the first definition of a matrix. And then Arthur Cayley in 1856, several years later, did a lot of work using matrices and explored them further to give us the inverse matrix. If you've ever done work with matrices, you know what I'm talking about. Matrix multiplication. He even was able to show that we could represent a matrix using a single letter, like the capital letter A or a capital letter B, and then we could perform mathematical operations on these letters, knowing that they represent a matrix of n dimensions, which is also very cool and valuable. In 1873, we needed to develop a new theory and use new mathematics in a way we hadn't previously to describe electromagnetism and its physical properties that we observe. And this also required the use of differential geometry, specifically as it relates to manifolds of higher dimensions. But linear algebra is differential geometry in 1 and 2 dimensions. It's flat differential geometry. And so this is where we were at in 1873. We also had the Lorentz transformations to describe space-time. And then finally in 1888, we have a modern definition of vector spaces, and we have the modern version that we use today of linear algebra, which of course has been advanced significantly since the start of the 20th century, with all of the developments and proofs within linear algebra. But the modern conception of it that we use today started with Peano in 1888, giving us our first precise definition of vector spaces. And so with that, that's a little bit of an introduction to linear algebra. And like I said, I would like to work on some videos applying these mathematics in the context of Newtonian mechanics. So with that, I'll end the video here, and we'll see you in the next one. Bye.